Welcome to Study Loop.
So for the part A of this problem, we need to evaluate the pressure of the gas at the point A. This is the point in the thermodynamical cycle. So for the process from C to A, the temperature will be constant as given in the problem. Therefore, while the pressure and the volume changes, the temperature stays constant, and we can use the next formula, PA VA equals PC VC. And this formula can be used to directly evaluate the pressure PA, because the pressure PA is the pressure that we need to find for this part of the problem. And the rest of the values are completely known. So PA equals PC times VC over VA. Substituting the known values, we obtain that it is 2 times 10 to the 5th power pascals, and here we will divide 0.04 and 0.01 meters cubed. This equals to pressure A equals 8 times 10 to the 5th power pascals. This is for the part A. This problem has 4 parts, so everything that we evaluate in the one part of the problem will be used in the another part of the problem. So parts are mutually interconnected. So for the part B, we need to find temperatures corresponding to the points A, B, and C of the thermodynamic cycle. So we will do this by deriving the formula for the temperature from the ideal gas equation. So ideal gas equation is PV equals to nRT. And from here, temperatures, the temperature actually is pressure times volume over nR. But this will be true for every temperature. So for the temperature TA, we can immediately substitute numeric values. This is 8 times 10 to the 5th. This is in pascals times 0.01. This is in meters cubed over 3.25 times 8.314. The final units will be in Kelvin, and TA will be 296 kelvins. Next, observe that the point C from the process CA, the temperature at the point C must be equal to the temperature at the point A, because this is the constant temperature process. We use that in the part A of the problem. So TC equals TA and equals 296 kelvins. And this means that we need to evaluate temperature on the point B using the derived formula nR, and this is equal to, again, substitute the numeric values, 8 times 10 to the 5th power times 0.04 meters cubed, and this is going to be 3.25 moles times 8.314 joules per mole Kelvin, and the final units is in units of Kelvin, so the final value is 1184 kelvins. Now we know temperatures at each point of the thermodynamic process, and this was asked in the part B of the problem. Now in the part C of the problem, we want to find out the value of the heat which enters and leaves the gas. So to find this heat, we need to find the heat corresponding to each part of the process. So for the process part AB, QAB. This process is happening under constant pressure, so we will use the constant pressure heat capacity. And the standard formula for this case, it will be number of moles times heat capacity under constant pressure times the change in temperature. So when we substitute the known values, we see that it is equal to 3.25 moles times 20.78 joules per mole Kelvin times the difference. And we know the temperatures. We know the temperature at the point B and at the point A. So it will be the temperature at the point B minus the temperature at the point A. And the total final units of this is in kilojoules. We will convert this into kilojoules. This will be just in joules. But for the final answer, we will convert this into kilojoules, and the QAB will be equal to 60 kilojoules. Because these values here turn out to be, when we calculate them, to be 60,000 joules. So it is easier to write it in the units of kilojoules. Now for the other part, where the heat is being exchanged, this is the part from B to C, and we are completing the process this way. So QBC, we have from A to B, and from B to C, and that is the complete thermodynamic process given here. So in this part of the process, the volume will be constant, so we will use CV for the heat capacity. This will be number of moles times CV times delta T, and we can substitute the values, so this will also be 3.25 times different value for the heat capacity, 47, times and the change in temperature, which is going to be from 296 kelvins minus 184 kelvins. Remember that the temperature at the point C is equal to the temperature at the point A. And here we are subtracting TB from TC. So this will also be in joules, but the final answer is better to be reduced to kilojoules. And when we evaluate it, it is negative, because of the temperature part, negative 36 joules. So in this part of the process, the system is giving out the heat, but in this part of the process here, it is getting heat in. And this is what we needed to express and evaluate for the part C of the problem. Now for the part D of the problem, we also need to find out in order to solve for the part D, before we actually go into part D, we will need to solve for one more heat, and we will derive this heat from the first law of thermodynamics. This is from the C to A. And this is going to be equal from the first law of thermodynamics, UCA plus WCA. And the internal energy here will be equal to 0, since the temperature is constant between C and A. Therefore, this is 0, and this is equal to the work done. The work done is equal to the area under the line on the pressure volume diagram, and this can be represented as 1/2. This is going to be half of the rectangle of the rectangular surface, PA plus PC, and this is going here to be VA minus VC. We can substitute the known values and see that it is 8 plus 2. This is for the pressures, over 2 times 10 to the 5th power pascals times 0.01 minus 0.04 meters cubed, and this finally equals Ca minus 15 kilojoules. This part was also important to be solved because in the part D we need to determine the change in internal energy for the whole system. So it was important to show that for between C and A, the total heat exchange will only equal to the work done, and it will the change in internal energy will be zero because the temperature is constant from between the point A and the point C. So for the part D, we only need to solve for two internal energy changes, from A to B and from B to C, and we can use standard formulas for this. So delta U AB equals N times CV TB minus TA. Substitute the known values numerically. 25 times 12.47 times the difference in temperatures, this will be in joules, and the final value will be AB equals 36 kilojoules. And for the internal energy change from B to C, we know this will happen under constant volume as well, so this will be equal to N times CV and the change in temperature here, which is equal to basically the same values numerically. Just we will inverse the temperature subtraction, so it will be the lower temperature minus the higher temperature. And we can observe immediately that UBC will be equal to minus 36 kilojoules. What this tells us? This tells us that delta U total for the whole process is equal to 0, and there is no change in internal energy. And this was to be expected because the whole process is cyclic. The beginning point and the ending point are one and the same, and therefore the change in internal energy will be 0. This is generally true for all thermodynamic processes. So this completes the problem. I hope you find this helpful, and I hope to see you in another lesson.